Hello guys, welcome you all. Today I will discuss about dual spaces of linear transformation and its properties and its subspaces, which is nothing but annihilator. Please don't forget to like and subscribe my channel. So let us start. First I will talk about isomorphism. Okay. Now what is isomorphism? In my previous lectures I have told about linear transformations, which is nothing but a mapping between two vector spaces over the same field. So here we have two vector spaces V and W over the field F. We say that V is isomorphic to W if there exists a linear transformation T V to W such that T is invertible. So T V to W, which is invertible linear transformation, then V is isomorphic to W, and this kind of linear transformation is called isomorphism from V to W. Now what happens if V and W are finite dimensional vector spaces? In that case, V is isomorphic to W if and only if dimension of V equals to dimension of W. So if now W is f to the power n, then we say V is isomorphic to f to the power n if and only if dimension of V is n. There are some other examples I have given. Please go through it. Now another one like this. Let V and W are finite dimensional vector space, okay, and T be a linear transformation. In that case, T is not isomorphism, as we don't know yet whether T is invertible or not. Suppose that beta is a basis for V. This kind of basis I have told you in my first lecture or second lecture. Then T is an isomorphism if and only if T beta is a basis for W. Think of my previous lecture. T V to W is linear and V and W are finite dimensional vector spaces. You have given a basis for the domain set, that is V, and it is called T is isomorphic if and only T beta is a basis for W. Why? Because when T beta is a basis for W, in that case T is 1 to 1. And as V is finite dimensional, so 1 to 1 implies T is on 2. So in that case T is invertible, and that's why these isomorphic properties hold. Let T V to W be linear transformation from a n-dimensional vector space V to a m-dimensional vector space W. So dimension of V and dimension of W are different. Beta and gamma are ordered bases for V and W respectively. Then rank of T is rank of LA and nullity of T is nullity of LA, where A is the matrix representation of T with respect to the ordered basis beta and gamma. Now what is linear functional? Till now we know linear transformation V to W, where both are vector spaces, or linear operator V to V. Now we are coming to another topic, that is linear functional. What is that? Let Vf be a vector space, then a mapping F V to F. Here the codomain set is the field F itself. This small f is called a linear functional on V if these properties hold. These properties include both the addition and multiplication property. Some examples also I have given here on linear functional that you can go through it. But the important example is, important example is this one. That is required in our dual space definition. What is that? So dual space based on the linear functional. A linear functional is a mapping from a vector space to its own field. Okay, under these properties. Got it? I hope you are understanding well. So let's go ahead. Let V be a finite dimensional vector space and beta be an ordered basis for V. This ordered basis now you know if you have followed my earlier lectures. For each I 1 to n, define f I x equals to ai, where ai's are nothing but the coordinate vector of x relative to the basis vector beta. Okay, because f is from V to f, so fx means x is a vector and fix equals to ai, where these ai's are given here. Then fi is a linear functional on V called the ith coordinate function with respect to beta. Fix, this fi, ith coordinate function with respect to the ordered basis beta. See, here I have mentioned a note. The linear functional fix, which is nothing but delta ij, play an important role in the theory of dual spaces. So now coming back to the definition of dual space. Okay, what is dual space? For a vector space V over the field F, we define the dual space of V to be the vector space LVF. This is not W, this must be F. LVF, set of all linear functionals from V to F, which is denoted by V star. This is called the dual space of V. So dual space of V, that is V star, is nothing but the set of all linear functionals from V to F, which we denoted by LVF. Note, dimension of V star is dimension of LVF, which you know, dimension of V into dimension of F. Now F is a field, so its dimension is always 1, so this is equals to dimension of V. So dimension of V star equals to dimension of V. V and V star are isomorphic. This is the reason why I told you about isomorphism. V and V star are isomorphic. So any linear transformation T V to V star is invertible. Theorem. What does it say? Suppose that V is a finite dimensional vector space with an ordered basis beta. Okay. Let Fi be the ith coordinate function. Here it is mentioned, ith coordinate function with respect to beta. Let beta star is f1, f2, dot dot fn. So the set of these ith coordinate functions. Then beta star is an ordered basis of V star. And for any f in V star, we can mention f like this. So V star, you got a vector space V star that is called dual space. And from this theorem, you are getting the basis of V star, which is depending on the basis of the vector space V. The ith coordinate functions Fi, then beta star is an ordered basis for V star, and any f in V star or dual space can be written like this. That is, it's simply like a generating set. Because it is a basis, so it is a generating set. Here I mentioned this dual basis that already I have told you. Another theorem, what does it say? Let's see. Let V and W be finite dimensional vector spaces over the field F with an ordered basis beta and gamma. Okay. For any linear transformation T V to W, the mapping T transpose. So now you are coming to the transpose of a linear transformation, and that is defined on dual space W star to dual space V star, and it is defined like T transpose G equals to G of T. Here it is written, which is also a linear transformation under this property this. So once you know a linear transformation T V to W, where V and W are finite dimensional, then you will have the matrix representation of T that I have mentioned in my last lecture. And from when you have a matrix, you must think about the transpose of that matrix. So the transpose of this matrix will given you the linear transformation from dual space of the codomain W star to the domain V star. And this is the unique linear transformation. An example I have given for better understanding. Please go through this example. If you have any problem, you can comment me. Now, once you have a dual space that is also a vector space, you know the basis, you must think of a subspace of it. To get the subspace, we must know what is annihilator. Let's read. Let V denotes a finite dimensional vector space. So care about this finite dimension and infinite dimension. Please be careful about these dimensions, because when it is finite dimensional, we say how it is isomorphic, and we define that basic properties theorems on linear, functional as well as dual space. So V be a finite dimensional vector space. So dimension of V is finite. For every subset S of V, the annihilator denoted by S naught. Here you can see S naught of S, as S naught is set of all elements from the dual space V star such that Fx equals to 0. You can relate this to your kernel of a vector space, and here it is the kernel of the dual space, that is called annihilator. These are the properties. First properties, S interior or S naught is a subspace of the dual space V star. But keep in mind, this S is not a subspace of V, it's simply a subset of V. Okay, from a subset you are defining the subspace, but that is not a subspace of V, that is a subspace of its dual space. If W is a subspace of V and X does not belongs to W, then there exists an F in W interior such that Fx not equals to 0. Okay, forget about this, there is some misprints. For any two subspaces W1 and W2, if they are equal, their annihilator must be equal. Now I am talking about subspaces of V. For any subspaces W1 and W2, the annihilator of W1 plus W2 equals to their individual intersection. So when this S becomes a subspace W, then we must have some properties like these two properties. These two properties based on subspace W. This you forget. There is some misprint. Now, if W is a subspace of V, then dimension of W plus dimension of W annihilator equals to dimension of V. And what does your rank nullity theorem says? Nullity of T plus rank of T equals to dimension of V. And here you are getting another definition of dimension W, that is, if W is a subspace and if you note its annihilator, then summation of their dimensions is equals to the dimension of V. Obviously V must be finite dimensional. Okay. Let T be a linear operator on V and W be a subspace of V. T linear operator and W be a subspace of V. Then W is T invariant. T invariant I have mentioned it earlier. Then W is T invariant if and only if W annihilator is T transpose invariant. This is very important property. T linear operator on V and W itself a subspace of V. Then W is T invariant if and only if W interior is T transpose invariant. Let another one, let V be a non-zero vector space and W be a proper subspace of V. Then there exists a non-zero linear functional AF such that Fx equals to 0. So you must have a non-zero functional if W is a proper subspace of V, where V is finite dimension. So last one, what does it say? Let V and W be non-zero vector spaces, may be finite or infinite dimensional over the field F, and T be linear. Then T is onto if and only if T transpose is 1 to 1 and T transpose is onto if and only if T is 1 to 1. So if you know the dual space, if you know the matrix representation on the dual spaces, from there you can say about the onto 1 1 property of the matrix representation on the linear transformation T. Here just see, if T is onto if and only if T transpose is 1 to 1. On the other hand, T transpose is onto if and only if T is 1 to 1. Okay? So, thank you very much for listening. If you have any problem, please comment me, or you can find the Telegram link of my group in the playlist. You can join there and ask me questions. Thank you very much.